Above your roof, planets are gliding along invisible highways, some boiling, some frozen, some hiding oceans or ancient scars. And tonight, you're joining that silent procession. Welcome to Misty Pulsex. If peaceful cosmic storytelling is your escape, subscribe and like. Now lie back. Our vessel is waiting at the edge of the sun, and what lies ahead is more incredible than you expect. Tonight, you're going on a quiet flight around the solar system. You don't have to move a muscle. You don't even have to stay awake. You can just lie where you are, let your eyes grow heavy, and let this story drift over you while sleep slowly catches up. If you drift off in the middle of a sentence, that's perfectly fine. The planets will keep circling, and the story will still be here when you come back. Right now, as you listen, you are already traveling through space at tens of thousands of miles per hour. Earth is quietly orbiting the sun at about 67,000 miles per hour, and the entire solar system is circling the center of our galaxy at more than 500,000 miles per hour. Somewhere out there on Mars, there is a volcano almost 3 times taller than Mount Everest, and closer to the sun there is a small world where one single day lasts almost twice as long as its year. You are already part of this strange, beautiful system of worlds, even if all you feel right now is the softness of your pillow and the slow rhythm of your own breathing. You don't have to remember any of those numbers. You can let them drift past like lights outside a train window at night. All that matters is the feeling that you are in motion, gently carried along with your planet, as we begin this slow night flight from the sun, past the inner rocky worlds, and onward into the wider, darker reaches of the solar system. Think of this journey as a quiet tour from the heart of our planetary family outward. We'll visit the sun, then glide past Mercury, then Venus, then our own Earth and Moon, and farther still to the red deserts of Mars. We'll pause over storms and canyons, listen to the silence over frozen craters, and watch thin rings of dust reflect the pale sunlight. At any moment along the way, you're free to stay, to wander, or to drift into sleep. Right now, as you lie here, you are already riding a spaceship. The Earth itself. If you could suddenly see the stars without the atmosphere, you'd notice that Earth is not still at all. We are moving in a nearly circular path around the sun, taking about 1 year to complete a single loop. That's our familiar year, made by this quiet, steady orbit. Even though the speed is enormous by everyday standards, the path is smooth and gentle, like a long, slow curve drawn in the dark. You don't feel the motion because everything around you shares it. The bed, the walls, the air, the trees outside, the oceans, the clouds. Everything is falling around the sun together, in a long, continuous curve. It's like being in an airplane cruising high above the clouds. Once the flight is steady, you don't feel the speed, only the calm. As you rest here, your entire world is tracing out a silent circle around the sun, one more loop in a pattern that has been repeating for billions of years. The solar system is mostly empty space, with a few tiny islands of rock and gas scattered across an enormous dark sea. If we could shrink the sun down to the size of a common door, the Earth would be about the size of a nickel floating roughly 100 feet away. The other planets would be even smaller and spaced out much farther. Everywhere in between, there would be almost nothing at all, just a thin scattering of dust and particles, drifting in a deep black ocean. This emptiness is what makes the solar system both peaceful and safe. The planets rarely come anywhere near each other. Each one follows its own quiet path, slowly looping around the sun, drawn by gravity the way a weight on a string circles your hand. They never need to hurry or fight for space. There is more than enough room for every world to glide. As you listen, you can imagine yourself floating in that darkness between worlds, wrapped in silence, watching the sun and planets drift like slow lanterns in a vast night. Our journey begins at the heart of this system, with the star that makes everything else possible, the sun. The sun is not a glowing disk painted on the sky. It is a real star, a giant sphere of hot gas, so large that more than 100 Earths could line up across its face. It holds almost all of the mass in the entire solar system, about 99 out of every 100 pounds of matter. Every planet, moon, and comet circles this one star, held in place by its gravity. The sun is made mostly of hydrogen and helium, the simplest elements, packed and squeezed to incredible pressures in its center. Deep inside, at its core, The gas is so hot and dense that hydrogen atoms are pressed together and fused into helium. In that process, a tiny bit of matter is turned directly into energy, the energy that becomes sunlight. It's a slow, steady kind of fire, not like a flame you see on Earth, but a quiet transformation happening all the time. Every second, the sun converts millions of tons of matter into light and heat, and yet it has enough fuel to keep shining at about the same brightness for billions of years more. To us, bathed in that light, it feels like a constant, dependable presence, the great lamp of the solar system. You don't need to picture the details of the nuclear reactions. You can just imagine a warm, endless sunrise, glowing at the center of everything, steady and patient. The light that warms your face on a sunny day left the sun only about 8 minutes ago. Sunlight travels at the speed of light, the fastest speed there is, crossing the 93 million miles between the sun and Earth in just a few minutes. That means when you look at the sun, never directly but through safe filters or in photographs, you are seeing it as it was 8 minutes in the past. In cosmic terms, that's almost live. But inside the sun, the story is very different. The energy created in the core doesn't stream straight outward. It takes a long, tangled path, bouncing from particle to particle, changing direction countless times. It can take 100,000 years or more for a packet of energy made in the sun's center to finally escape and emerge as sunlight. So the light that gently brightens your mornings was first born deep inside the sun when ice ages came and went on Earth, when early humans were just beginning to walk across the continents, and even long before that. The sunlight on your skin carries a memory of very ancient times. If you like, you can imagine each warm ray as a traveler who has wandered through the sun for ages, only to arrive here tonight, in time to fall softly across your closed eyes and your resting body up close. The surface of the sun would not look smooth, but like a slow, boiling ocean of light. The layer we see with our eyes is called the photosphere, the light sphere. A thin shell compared to the whole star. If you could watch it safely through a powerful telescope, you'd see a pattern of tiny, bright cells, like the surface of a pot of water just beginning to simmer. These cells are enormous columns of hot gas rising, cooling slightly, and sinking again, in a constant gentle cycle. Scattered across this surface are darker patches we call sunspots. They look dark only by comparison, because they are a bit cooler than the surrounding areas. Each one can be wider than Earth itself. These spots are linked to the sun's magnetic fields, which twist and loop through the gas, sometimes sending arcs of plasma arcing high above the surface in great curved loops. Even though these structures are huge, their motion is slow and graceful from a human point of view. A loop of glowing gas might rise and fall over hours or days. A group of sunspots might drift and change over weeks. The sun is always in motion, but its changes unfold with a calm, steady rhythm. You can picture the sun's surface as a vast, glowing ocean, always stirring, but never in a hurry, simmering quietly in the dark. The sun has seasons of activity too, a gentle rhythm that lasts about 11 years. Over this cycle, the number of sunspots on the surface rises and falls. At times, they are plentiful, scattered across the face of the sun like freckles. At other times, the surface is almost spotless. These cycles are tied to the sun's magnetic field, which slowly twists and reorders itself over many years. When the sun is more active, it sometimes sends out stronger bursts of particles and energy. Occasionally, these reach Earth and interact with our planet's magnetic field and atmosphere. On the night side of Earth, especially near the poles, these invisible streams of particles can create shimmering curtains of color in the sky, the auroras, the northern and southern lights. Even though these processes involve enormous amounts of energy, they are very gentle from our point of view, happening many millions of miles away. Our planet has its own shields and layers of protection that keep life safe at the surface. Most of the time, you notice none of this. The sun simply rises and sets, day after day, while these long cosmic breaths play out in the background. As you relax, you can imagine the sun slowly breathing in and out over decades, its magnetic fields curling and uncurling, while our little world keeps peacefully turning in its light. The sun does not end sharply at its visible edge. It has an invisible atmosphere that stretches far into space. Above the photosphere is a hotter, thinner region called the corona, which you can only see clearly during a total solar eclipse, when the moon blocks out the bright disk. Then, faint white streamers appear, spreading outward in all directions like soft, feathery wings of light. This corona is much hotter than the sun's surface, extending millions of miles into space. From this hot outer atmosphere, particles are constantly streaming away in all directions. This is the solar wind, a thin, gentle flow of charged particles that fills the space between the planets. It's not like wind you feel on your face. Out in space it is incredibly thin, much thinner than the best vacuum we can make on Earth. But over vast distances, this wind shapes the tails of comets, pushes dust, and inflates a great bubble around the solar system called the heliosphere. Our entire planetary system is wrapped in this subtle flow of particles, like a ship inside a protective wake as it moves through the galaxy. The solar wind is always there, whispering past every planet, touching everything, silently connecting us all back to the sun. As you drift toward sleep, you might think of the solar wind as a very soft cosmic breeze, flowing past our quiet spacecraft as we begin to turn away from the sun and head toward the innermost planet, Mercury. Mercury is the small, dense world that lives nearest to the sun. If you could see it up close, Mercury would look a little like our moon, a gray, heavily cratered sphere, scarred by countless impacts from ancient asteroids and comets. But Mercury is slightly larger than the moon, with a diameter of about 1/3 that of Earth. For its size, it's surprisingly heavy, because much of Mercury is made of metal. It's as if someone carved away the outer layers of a larger planet and left behind a big iron heart. Underneath its rocky crust, Mercury has a huge iron core that makes up a larger fraction of its volume than any other planet in the solar system. This dense core gives Mercury a strong pull for its size and even a weak but real magnetic field, a sort of ghostly echo of Earth's much stronger one. That magnetic field tells us that at least part of Mercury's core may still be molten and slowly moving. You can imagine Mercury as a compact, iron-rich world, a small but stubborn planet, circling close to the warming fire of the sun. Mercury moves faster around the sun than any other planet, finishing a full orbit in just about 88 Earth days. That means a year on Mercury, one trip around the sun, is less than 3 months long by our calendar. But Mercury spins very slowly on its axis. It rotates just 3 times for every 2 trips around the sun. This strange pattern means that from the surface of Mercury, the time from one sunrise to the next is about 176 Earth days. A single solar day on Mercury lasts almost 2 of its own years. If you were standing on Mercury's surface in your protective spacesuit, you would see the sun rise very slowly, inching above the cratered horizon. The sun would look about 3 times larger than it does from Earth, burning fiercely in the dark sky. It would take weeks and months for it to crawl overhead, and months more for it to set. Half of your long Mercurian day would be spent in a blazing, unending morning, and half in a drawn-out, fading afternoon. On Mercury, the rhythm of days and nights is stretched and slowed, like time itself is taking deep, careful breaths between each sunrise and sunset. The temperatures on Mercury swing between some of the most extreme highs and lows in the solar system. Because it is so close to the sun and has almost no atmosphere, the side facing the sun can heat up to temperatures hot enough to melt lead. The ground bakes under the harsh sunlight, with no air to spread the heat around or soften the glare. There are no clouds, no breeze, no blue sky, only a black sky and a relentless sun. But on the night side, the story is very different. With no thick blanket of air to hold the heat, the warmth radiates away into space. Temperatures plummet to hundreds of degrees below freezing, colder than some places in the outer solar system. The same ground that was scorching hot in the endless day becomes bitterly cold in the endless night, over and over again. On Mercury, just by turning from day to night, you pass from furnace to freezer. The planet lives in extremes, yet it follows this pattern calmly and predictably, cycle after cycle, without hurry or complaint. You don't have to feel those sharp contrasts. From our gentle distance, Mercury's hot days and frozen nights are just another quiet rhythm, like waves of heat and cold passing through a silent stone. Mercury's surface records billions of years of cosmic history in its craters and cliffs. Looking down from orbit, you'd see round impact craters of all sizes, overlapping and crowding one another. Some are tiny, just a few yards across. Others are vast basins, hundreds of miles wide. One of the largest is called the Caloris Basin, a huge circular scar created long ago by a colossal impact. After that impact, waves of energy rippled through the planet's crust, and on the opposite side of Mercury, the surface buckled and fractured, creating a region of jumbled, weird terrain. Scattered across Mercury's face are also long, curved cliffs called scarps. These cliffs can be hundreds of miles long and thousands of feet high, where the crust has been pushed together and forced upward. They formed as Mercury's interior slowly cooled and shrank, like a drying apple wrinkling over time. The outer shell had to fit a slightly smaller core, and so it folded and cracked. When you look at Mercury's landscape, you are looking at a memory of its entire life. A record of impacts, cooling, and slow change, written in stone across billions of quiet years in the shadows at Mercury's poles. There may be water ice that never sees the sun. Near the North and South poles, some large craters are oriented in such a way that their floors remain in permanent shadow. Because Mercury's axis is not tilted very much, the sun never rises high above the horizon there. The crater rims block the light, and the interiors stay dark and cold, even while other parts of the planet bake. Radar observations have shown bright reflections from these dark craters, and the simplest explanation is deposits of water ice. That water may have arrived long ago on comets and icy asteroids, or it may have been released from Mercury's interior and then trapped in these cold, shadowed pockets. Here, just a short distance from a star that blazes in a black sky, there are places cold enough for ice to survive for millions, maybe billions of years. It's a quiet paradox. A world of fierce heat that still shelters cold, frozen reservoirs, hidden in everlasting shadow, patiently waiting in the dark. Mercury has no thick atmosphere like Earth's, only a sparse exosphere, a whisper of atoms hovering above the surface. There is no air to breathe, no wind to shake the rocks, no clouds to form and drift. A few stray atoms of sodium, oxygen, helium, and other elements float above the ground, knocked off the surface by sunlight, micrometeor impacts, and the solar wind. Because these particles are so widely spaced, they rarely bump into each other. It's closer to a vacuum than any vacuum chamber we can build on Earth. With no significant atmosphere to protect it, Mercury's surface is exposed directly to space. The planet is lightly sandblasted by tiny particles from the sun and from interplanetary dust. Over millions of years, this slow, gentle bombardment darkens the rocks and smooths some of the sharp edges of craters, giving the surface a somewhat muted, weathered look. From above, you can imagine Mercury as a quiet, airless world, lying bare under the sun, wrapped only in the thinnest possible veil of gas. More a suggestion of an atmosphere than a real one. We know Mercury's secrets thanks to a few patient robotic visitors that have flown past and orbited this hidden world. The first close-up images of Mercury came from a spacecraft called Mariner 10 in the 1970s. It performed a series of flybys, mapping about half of the planet's surface and revealing its cratered, moon-like face. For decades afterward, that was all we knew in detail. Half a world, half a story. Later, another spacecraft, called Messenger, slipped into orbit around Mercury. It spent several years circling the planet, carefully measuring its gravity, its magnetic field, its surface composition, and its thin exosphere. Messenger slowly built a complete map, filling in the missing half and adding layers of detail. It found evidence of those polar ice deposits, mapped the scarps and basins, and helped us understand Mercury's oversized metal core. Now, another mission is on its way, a joint European and Japanese spacecraft called Bepi-Colombo, which will perform flybys and eventually orbit Mercury as well. It will add new information to this growing picture. Even when we are not looking, when we are asleep, these silent machines keep circling in the dark, listening and watching. You can imagine them gliding over Mercury's battered surface in endless loops, their instruments quietly awake while the planet itself remains utterly still. From our imaginary window in this night ship, Mercury is a small, gray sphere, half in sunlight and half in darkness, forever turning slowly. We watch it shrink as we gently fire our engines and begin to slide outward, away from the blazing proximity of the sun. The light softens as the distance grows. The sun becomes a little smaller, a little less overwhelming in the window, but still bright enough to paint everything with a silent brilliance. Between Mercury and the next planet, Venus, there is only space, vast, quiet, almost completely empty. Dust particles drift lazily. The solar wind streams past. There are no signs, no landmarks, only the changing positions of the sun and the tiny points of light ahead. You don't have to navigate. You don't have to steer. You can simply rest in your seat, feel the slight hum of our imagined engines through the floor, and watch Mercury recede into the dark, becoming just one more faint wandering star. As we glide outward, it helps to remember that these worlds are like beads on an invisible string. Each planet follows its own path, inward or outward, slow or faster, but all chained together by the sun's gravity. Mercury, Venus, Earth, Mars, they are part of a single system, a family that formed from the same swirling disk of gas and dust billions of years ago. Each one has its own character, its own rhythms, its own history written into its rocks and skies. We have just visited the smallest, hottest, most exposed of the inner planets, a dense iron world close to the fire. Ahead of us now lies Venus, bigger, brighter, wrapped in thick clouds, and after that, our own familiar Earth and its moon, turning quietly beneath a thin blue veil of air. As you breathe slowly and your eyes grow heavier, you can feel yourself carried along with us, floating weightlessly between Mercury and Venus, halfway between what we've seen and what we're about to see. You don't need to hold on to all the details of Mercury's long days or its hidden ice, or the sun's boiling surface and invisible wind. Those facts are like stars. You don't have to count them to feel that the sky is full. Instead, you can let them sink into the background, forming a soft, dim glow behind your thoughts. If you remember only the feeling, the idea of a small, cratered iron world swinging close to a golden star, that is more than enough. The solar system is patient. It will be here tomorrow, and a billion tomorrows from now. The planets will still be circling. The sun will still be shining. And you, on your small blue world, will still be able to look up and imagine where they are and what they look like. For now, you can let your breathing slow, feel the weight of your body supported, and picture our ship coasting silently through the dark, leaving Mercury behind as a fading memory, and turning its nose toward the soft golden glow of Venus. Venus is the brightest planet in our sky, yet its surface is hidden under an unbroken roof of clouds. From Earth, Venus often appears as the evening star or the morning star, a bright white point hanging low near the horizon just after sunset or before sunrise. It outshines every other planet and even most stars, not because it's the biggest, but because those thick clouds reflect so much sunlight. If you've ever noticed a single bright object near the twilight horizon and wondered what it was, there's a good chance you were looking at Venus. As our imaginary ship glides outward from Mercury's orbit, Venus grows into a creamy, glowing disk. Up close, the planet looks smooth and featureless in visible light, wrapped in layers of pale yellow-white cloud. There are no gaps to peek through, no blue sky, no visible land. The entire world is tucked under a permanent blanket, like a bed pulled up over a sleeping planet. From space, Venus looks peaceful and soft, like a glowing pearl drifting around the sun, even though a very different story is unfolding far below the clouds. Venus is almost the same size as Earth, but the two worlds could hardly feel more different. In terms of diameter and mass, Venus is often called Earth's twin. If you put the two planets side by side, they'd look like siblings. Nearly the same size, made of rock, with iron cores and solid crusts, orbiting the same star. But where Earth's surface is cooled by oceans and protected by a relatively gentle atmosphere, Venus's surface is wrapped in a dense blanket of carbon dioxide-rich air. Near the ground, this atmosphere is so thick that the pressure would feel like being deep under an ocean on Earth. The gases trap heat extremely well, creating a strong greenhouse effect. As a result, the surface of Venus is hotter than that of Mercury, even though Venus is farther from the sun. Temperatures are high enough to melt lead, and they stay that way everywhere, day and night, pole to equator. You don't have to picture the exact numbers or worry about them. You can just imagine that under those soft-looking clouds lies a rocky world that is permanently warm, wrapped in its own heavy, insulating blanket, never cooling, never changing temperature with the seasons like Earth does. On Venus, the sun rises in the west and sets in the east, and a day is longer than a year. Venus spins very slowly and in the opposite direction to most other planets, including Earth. It takes about 243 Earth days for Venus to complete one full turn on its axis, but only about 225 Earth days to go once around the sun. That means a Venusian day, the time from one sunrise to the next, is longer than a Venusian year. Because it spins backward compared to its orbit, if you stood on the surface of Venus, inside a very protective suit, you would see the sun creep up from the western horizon and sink slowly in the east. The sky would change very slowly, the light crawling across the landscape over months. There would be no quick sunrises, no short evenings, just long, drawn-out transitions between day and night, filtered through the dense clouds overhead. In this strange arrangement, time seems to stretch out. On Venus, the rhythm of rotation and revolution is so slow and unusual that a lifetime might feel like one extended, hazy day. High above Venus's hidden surface, the clouds race around the planet at superfast speeds. Although the solid body of Venus spins very slowly, its upper atmosphere moves much faster. At heights of about 40 to 70 miles above the surface, strong winds push the clouds around the planet in just a few days. This superrotation means the atmosphere laps the planet's surface many times over in the span of a single Venusian day. The clouds themselves are made mostly of tiny droplets of sulfuric acid mixed with other compounds, suspended in a thick layer. Sunlight filters through them and scatters, giving Venus its soft, pale appearance from space. From our ship, if we switched to special instruments, we'd see bands and swirls, subtle patterns in the cloud tops, like slow-moving storms frozen in place. If you imagine floating with a balloon in the upper atmosphere of Venus, you'd be carried around the planet in a continuous, smooth wind, circling again and again, far above the hidden rocks and valleys below. The world beneath would stay out of sight, but the sky around you would move in a constant, steady stream. Although no human eye has looked directly at Venus's landscape, our machines have peered through the clouds. Because visible light cannot penetrate the thick atmosphere, we had to use radar to map the surface of Venus. Spacecraft such as Magellan sent radio waves down through the clouds and listened for the echoes, building detailed maps of the terrain. Those maps reveal highlands and lowlands, vast plains of solidified lava, and long, sinuous channels where molten rock once flowed. We've also sent a few hardy landers, especially from the Soviet Venera program. They descended through the crushing atmosphere and survived only minutes on the surface before the heat and pressure overwhelmed them. In those brief windows, they sent back images of a dim orange landscape. Flat rocks, scattered stones, and a hazy sky tinted by the thick air. No water, no plants, just bare rock under a heavy, hot sky. Yet even here, in such extreme conditions, the planet's geology follows understandable rules. Rocks form, melt, and solidify. Mountains rise, plains spread out. Venus may not be comfortable, but it is still a world with a story written in its stones. Some scientists suspect that long ago, Venus might have had oceans and a cooler climate, perhaps not so different from early Earth. Over time, for reasons still being studied, something changed. Maybe the sun brightened, maybe greenhouse gases built up, maybe volcanic activity reshaped the atmosphere. Whatever happened, Venus gradually became the hot, dense world we see today. The hypothetical oceans evaporated, water molecules broke apart, and the lighter hydrogen escaped into space, leaving a dry, baking surface behind. We can't go back and watch that slow transformation, but we can read hints of it in the atmosphere's composition and in the surface features revealed by radar. Venus reminds us that planets are not frozen in time. They evolve, sometimes gently, sometimes dramatically, over billions of years. As you lie here, you can think of Venus as a quiet, cloud-wrapped planet that has already had a long and complex life, turning slowly near the sun, its current calm hiding a restless past. As we leave Venus behind, a blue-white marble waits ahead in the dark. Our ship continues outward, crossing the imaginary line of Earth's orbit. At first, Earth is just another star-like point in the black, but as we draw closer, it swells into a sphere. A patchwork of oceans and continents, swirls of cloud, and the faint glow of air. Near it, a smaller gray companion circles steadily. The moon, bound to Earth by gravity in a long, shared dance. From this vantage point, the Earth-Moon system looks like a tiny double jewel, a bright planet with a pale satellite, both caught in the sun's gentle pull. On the night side of Earth, city lights shine along coasts and rivers. On the day side, sunlight glints off ocean waves and snowy peaks. We are looking back at your home now, seeing it as it truly is, a small living world in a vast quiet space. From space, Earth looks like a world made mostly of water and light. More than 2/3 of Earth's surface is covered by oceans, deep, connected bodies of water that wrap around the planet like a dark blue skin. Thin white curls of cloud drift above them, casting soft shadows on the waves below. Here and there, continents break the surface, showing patches of green, tan, and white where forests, deserts, and ice caps lie. The atmosphere around Earth scatters sunlight in a way that makes the sky look blue from the ground. From orbit, that atmosphere is a delicate, pale shell, just a few dozen miles thick compared to the planet's size. It is easy to see how thin it really is. All of our weather, all of our breathable air, all of our clouds and rain and snow are contained in that fragile-looking layer. Against the black backdrop of space, this glowing blue shell and the shimmering oceans beneath it look both robust and delicate, like a soap bubble floating in the dark. Earth's gentle tilt and steady spin shape the seasons that mark our lives. Our planet's axis is tilted by a little more than 23 degrees relative to its path around the sun. That tilt means that as Earth orbits, different regions lean slightly toward or away from the sun over the course of a year. When your hemisphere tilts toward the sun, you experience longer days and warmer seasons. When it tilts away, you enter the quiet, darker months. Earth rotates once every 24 hours, giving us the familiar cycle of day and night. Combined with its roughly 365-day orbit around the sun, this rotation lays out the structure of time that most of our calendars and daily routines follow. Sunrise, midday, sunset, midnight. These are all just reference points on Earth's continuous turning. From far away, you can watch Earth spin like a slow, steady top, its tilted axis drawing a gentle circle over thousands of years, while the pattern of seasons repeats again and again. A thin, invisible shell of air and magnetism makes Earth feel like home. The air you breathe is a mixture of nitrogen, oxygen, and traces of other gases. This atmosphere softens the sun's rays, keeps heat from escaping too quickly at night, and helps maintain temperatures that allow liquid water to exist on the surface. Without it, Earth would be a cold, airless rock, more like the Moon or Mercury. Surrounding Earth is also a magnetic field, generated by the movement of molten metal in its outer core. This field extends far into space, forming a protective bubble called the magnetosphere. When charged particles from the solar wind reach Earth, many are deflected by this magnetic shield. Some are guided toward the poles, where they interact with the upper atmosphere to create auroras, ribbons of green, red, and purple light that shimmer in polar skies. You may never see these lights in person, but knowing they are there, delicate curtains of color quietly rippling over the dark, adds an extra layer of peaceful beauty to the world you live on. Somewhere on that turning globe, you are lying under a roof, listening to this story. From our high vantage point, the details of your individual life are invisible. We see no houses, no streets, no names. We see only clouds, oceans, landmasses, and the thin layer of air that people, animals, and plants all share. But we know that down there, in one tiny spot on that slowly rotating sphere, your body is resting, your chest rising and falling, your mind wandering among these images of distant worlds. You are part of this planet's story. Your heartbeat syncs with its day and night cycles. Your memories are made under its skies. Even while you sleep, Earth continues to turn. The sun will rise and set whether you watch it or not, and the stars will come and go above your roof. Right now, you are both very small, one person in a vast universe, and very special. A conscious passenger on this blue world's long, quiet voyage around the sun. Earth has one large moon, and it always shows us the same face. The moon orbits Earth at an average distance of about 250,000 miles. It rotates once on its axis in the same amount of time it takes to complete one orbit around Earth. This synchronous rotation keeps the same hemisphere facing us at all times. When you look up at the moon from Earth, you are always seeing familiar patterns. The dark seas, the lighter highlands, the same set of craters arranged like a calm, unchanging face. On its far side, the side we never see directly from the ground, the moon looks different, more heavily cratered, with fewer of the dark lava plains we call Maria. Spacecraft have mapped this hidden hemisphere, but to the naked eye, from your backyard or your window, the moon's near side is all you will ever see. This gentle lock between Earth and its moon is like an old dance, the two bodies turning together in a steady rhythm that has persisted for billions of years up close. The moon is a world of gray dust, bright highlands, and dark lava seas. If we drift closer in our ship and slip into orbit around the moon, its surface comes into clearer focus. Large, dark plains, the Maria, are ancient lava flows that filled huge impact basins long ago. They are smoother and less cratered than the surrounding terrain, and from Earth, they give the moon its familiar patterns and shapes. The lighter-colored highlands are older and more heavily cratered. Countless impacts over time have broken rocks into fine powder, creating a layer of loose material called regolith that covers most of the surface. There is no wind to smooth things out, no rain to wash dust into valleys. Craters can remain almost unchanged for millions, even billions of years. Standing on the moon, you would see a black sky, even in direct sunlight, because there is no thick atmosphere to scatter light. The sun would glare overhead, and stars would be visible all around. The horizon would be closer than on Earth, curved and abrupt, with jagged mountains and crater rims breaking the line between gray ground and starry sky. The moon is likely born from a collision, and it has been shaping Earth ever since. The most widely accepted idea is that early in Earth's history, a Mars-sized object collided with our young planet. The impact threw large amounts of molten rock into orbit, where it eventually clumped together and cooled into the moon. That would explain why the moon's composition is similar to Earth's outer layers, and why Earth and moon are so closely bound. Since then, the moon has exerted a gentle, steady tug on Earth's oceans, creating tides that rise and fall each day. Over long periods, this tidal interaction has slowed Earth's rotation slightly and pushed the moon gradually farther away. The moon also helps stabilize Earth's axial tilt, preventing wild swings that might have made our climate much less stable over geologic time. You can think of the moon as both a companion and a quiet caretaker, its steady pull helping to keep Earth's environment within a range that has allowed life, including you, to flourish. For a brief moment in cosmic time, humans walked across the moon's surface. In the late 1960s and early 1970s, astronauts from Earth traveled to the moon, landed, and explored several sites on the near side. They collected rocks, set up experiments, and left footprints in the dust. With no wind or rain to erase them, those footprints could last for millions of years, slowly softened only by micrometeorite impacts and the steady rain of tiny particles from space. From orbit, you might glimpse the faint traces of these visits. The bases of landing craft, reflective instruments, small disturbances in the dust. They are tiny scars compared to the moon's great impact basins and mountain ranges, but they represent something remarkable. A moment when beings from one world reached out and touched another. As you drift toward sleep, it can be comforting to remember that even though we are small and our lives are short, we have already reached beyond our home planet, one careful step at a time. Leaving the Earth-Moon pair behind feels like stepping away from a warm campfire into the wider night. As our ship pulls back, Earth and the moon shrink together, the distance between them compressing into a thin line of pale light. The blue of the oceans, the white of the clouds, the gray of the moon, all merge into a double point that gradually becomes just one more bright star in the darkness behind us. Ahead lies a redder world. Mars, with its dusty deserts, towering volcanoes, and canyons that could stretch across entire continents on Earth. The space between Earth and Mars is mostly emptiness, thin gas, scattered dust, occasional asteroids moving in their own patient orbits. As we aim our course outward again, You can stay awake and follow every detail, or you can allow your mind to soften, letting Earth, the Moon, and Venus sink into the background of your thoughts, like three small lanterns glowing faintly behind you in the dark. The solar system continues its endless turning, regardless of whether your eyes are open. Earth goes on spinning, the Moon keeps circling. Venus glides along its inner orbit, forever wrapped in clouds. On the surface of your planet, tides rise and fall, clouds gather and fade, people wake and sleep, all under the same sun we visited earlier. You are aboard this night flight as long as you want to be. At any time, you can imagine looking back at that blue world and its gray companion, knowing that somewhere down there, your sleeping body is being carried gently around the sun, rocked by gravity and time. Ahead, Mars waits, surrounded by the thin pinkish glow of its own fragile atmosphere, its rusty plains illuminated by a distant sunday. Our next steps will take us there. Mars is a cold desert world, but it once had rivers and lakes. As our night ship leaves the orbit of the Moon and glides outward, the bright blue of Earth fades behind us, and ahead we see a tiny reddish point shining in the darkness. That is Mars, the next planet out from the Sun. As we draw closer, that point grows into a small disk, then into a world, rust-colored with dark patches and white caps at the poles. It is smaller than Earth, about half its diameter, and only 1/10 of its mass, but it has mountains, valleys, volcanoes, and polar ice, just as Earth does. Mars orbits the Sun at a greater distance than Earth, taking about 687 Earth days to complete 1 year. The sunlight there is weaker, the shadows softer, and the temperatures on average are much colder. Its atmosphere is thin, made mostly of carbon dioxide, with only traces of water vapor and other gases. From orbit, the sky over Mars looks like a thin, reddish veil over an immense, ancient landscape. You can imagine Mars as a quiet, dusty cousin of Earth, a smaller, colder world that hints at a warmer past carved into its rocks. On Mars, there is a canyon so long it could stretch across an entire continent on Earth. As we drift into orbit, one feature dominates the equatorial region. Valles Marineris, a system of canyons thousands of miles long. If you laid this canyon complex across North America, it would reach from coast to coast. Some sections are up to 4 miles deep and as wide as several hundred miles. The walls drop steeply to shadowy floors where landslides and layered rock are frozen in time. Scientists think Valles Marineris may have begun as a great crack in the crust, related to stresses from nearby volcanic uplifts, and then widened and deepened over time through erosion and collapse. Whatever its exact origin, it is a scar on a planetary scale, a reminder that even seemingly solid worlds can stretch and fracture over millions of years. If you could float just above the canyon, you would see cliff faces disappearing into bluish haze, ridges fading into the distance, and a horizon carved not by oceans, but by stone. There would be no river at the bottom now, only dust and rock and the thin whisper of Martian air. The canyon lies there in silence, a giant wound in the crust of Mars, patiently telling a story of tension and time. Mars also holds the tallest known volcano in the solar system. On the western side of Mars stands Olympus Mons, a shield volcano so large that it would cover an entire region the size of a small country. Its base spans hundreds of miles, and its summit rises more than twice as high as Mount Everest. The slopes are very gentle, so if you tried to walk up them, it would feel like a long, drawn-out uphill rather than a steep climb, but the distance is immense. Mars's lower gravity and lack of plate tectonics helped Olympus Mons grow so large. On Earth, tectonic plates move over volcanic hot spots, creating chains of islands and mountains. On Mars, the crust stayed mostly still over its hot regions, allowing lava to pile up in one place over millions of years. Each eruption added another thin layer of solidified rock, building the volcano higher and wider until it became the giant we see today. Imagine standing on its summit in a protective suit, looking out across a horizon that curves noticeably with the planet, the base of the volcano hidden far below. The sky would be a butterscotch color, the sun a smaller disk, and all around you, the landscape would fall away into the rusty plains of Mars. Even as you relax here on Earth, Olympus Mons stands watch over the Martian desert, its great slopes frozen in place under a thin, chilly sky. The surface of Mars is a world of rust-colored deserts, thin air, and polar ice caps. From orbit, Mars appears mostly red and orange because its rocks and dust contain iron minerals that have oxidized, essentially rusted over time. Wind, though thin, is still strong enough to lift and carry this fine dust across the planet, creating drifting dunes and hazy skies. Darker regions are often areas where the wind has swept the dust away, revealing older basaltic rock beneath. At the poles, bright caps of ice stand out against the reddish ground. These caps are made of both water ice and frozen carbon dioxide, also known as dry ice. In winter, the polar regions grow as carbon dioxide from the atmosphere freezes onto the surface. In summer, some of that dry ice sublimates back into gas, shrinking the caps and slightly thickening the atmosphere. This seasonal breathing in and out is slow but steady. Occasionally, dust storms grow large enough to envelop much of the planet, softening shadows and turning the sky a deeper, more uniform color. Even these global storms unfold gently on human timescales, lasting weeks or months, then gradually settling as the dust falls back to the ground. Ever so slowly, grain by grain, Martian winds reshape the surface, while the polar ice quietly waxes and wanes with the planet's long seasons. A day on Mars is only a little longer than a day on Earth. Mars rotates on its axis in just over 24 hours and 37 minutes. Mission planners and scientists who work with Martian landers often talk about sols instead of days, each sol being one Martian rotation. This near match to Earth's day makes Mars feel familiar in a way that Venus or Mercury do not. The sun rises and sets in a similar pattern, casting shadows that shift in a rhythm not far from what we know. Mars is also tilted on its axis by about 25 degrees, close to Earth's 23.5-degree tilt. As a result, it experiences seasons, with its polar regions leaning toward and away from the sun over the course of its orbit. But because Mars's year is nearly twice as long as Earth's, these seasons last much longer. A Martian summer or winter in any given region stretches out over many months. If you were living on Mars, you could still talk about spring, summer, fall, and winter, and you could still watch the sun trace low arcs in the sky in winter and higher arcs in summer. The pattern would be familiar but slower, as if time had been gently stretched. On Mars, the cycle of days feels a lot like home, while the years slip by more leisurely, in long, quiet seasons. Today Mars is dry and cold, but its rocks remember a time when water flowed. Even though liquid water cannot last long on the surface now, signs of ancient water are carved into the landscape. Networks of dried river valleys twist across the plains, branching and merging in patterns that look very much like river systems on Earth. In some craters, you can see what appear to be old shorelines and deltas, formed where water once collected into lakes. Orbiters and rovers have found minerals that typically form in the presence of liquid water, such as certain clays and sulfates. Layered sedimentary rocks suggest that standing bodies of water persisted long enough to lay down strata over time. Some regions show evidence of catastrophic outflows, where huge volumes of water may have surged across the surface, leaving behind scoured channels and chaotic terrain. Billions of years ago, Mars likely had a thicker atmosphere and a warmer climate, allowing water to exist in lakes, rivers, and perhaps even a shallow ocean in its northern lowlands. Over time, that atmosphere thinned, the surface cooled, and the water either evaporated into space, froze in the ground and polar caps, or retreated deep beneath the surface. While you breathe easily under Earth's sky, Mars holds its breath, keeping the memory of ancient lakes and rivers quietly locked inside its rocks. We know Mars so well because we have sent a small fleet of robots to wander its surface. For decades, orbiters have circled Mars, mapping its terrain, measuring its atmosphere, and looking for hints of water and ice. Landers have touched down and sampled the soil. Rovers, small, car-sized robots, have trundled slowly across the ground, sending back images and data. They move cautiously, often taking years to travel distances that a person could walk in an afternoon, because each step is planned and commanded from many millions of miles away. Rovers like Spirit and Opportunity explored for far longer than expected, climbing hills and examining rocks that told stories of ancient water. Curiosity continues to navigate a large crater, studying layers of rock that record environmental changes over long stretches of time. Newer rovers, like Perseverance, explore old lake beds and collect samples that may someday be brought back to Earth for deeper study. High above, orbiters relay these signals, acting as intermediaries between the rovers and Earth. Together, they have given us a remarkably detailed view of this distant desert. Panoramas of rocky plains, close-ups of dust grains, and even the sound of Martian wind whispering past a microphone. While you rest, these tireless machines continue their slow, careful work on Mars, turning wheels and pointing cameras under a pale, hazy sky. Mars has 2 tiny moons that look more like captured asteroids than miniature planets. Phobos and Deimos, Mars's moons, are small, irregularly shaped bodies that orbit close to the planet. Phobos, the larger of the two, is still only about 14 miles across at its widest. It circles Mars very quickly, completing an orbit in just a little more than 7 hours, so it rises in the west and sets in the east several times during a single Martian day. Deimos is smaller and farther away, moving more slowly across the sky. Their surfaces are dark and heavily cratered, with grooves and ridges created by impacts and stress. Because they are so small, their gravity is very weak. A person standing on Phobos and jumping gently could launch themselves into space and never return, leaving the little moon behind with a single soft push. Phobos is gradually spiraling inward toward Mars and is expected, far in the future, either to crash into the planet or to break up and form a temporary ring. Deimos, on the other hand, is drifting slowly outward. Both moons, in their different ways, are participating in a long, slow reshaping of the Martian system. You can picture these 2 little companions as silent stones looping around Mars, their paths slowly changing over millions of years, barely noticed from the vast distances between the planets. Beyond Mars, the space between the planets is filled with countless small worlds, the asteroids. As our ship leaves the rust-colored planet behind, we approach a broad region between Mars and Jupiter where many rocky bodies circle the Sun. This is the main asteroid belt, a zone of small and medium-sized objects that never came together to form a full-sized planet. Gravity from Jupiter and other factors kept this material from gathering into one large world. Despite the number of asteroids, the belt is mostly empty space. The objects are spread out over such a large volume that you could travel a long way and never come close to one unless you aimed for it. They range from dust grains to bodies hundreds of miles across, each following its own path around the Sun, shaped by gravity and gentle nudges over eons. Drifting through the asteroid belt is less like weaving through a field of boulders and more like sailing across a vast, dark ocean where distant islands occasionally appear on the horizon. One of these small worlds, Ceres, is big enough to be called a dwarf planet. Ceres is the largest object in the main asteroid belt, roughly 600 miles wide. Its gravity has pulled it into a nearly spherical shape, which is one of the reasons we classify it as a dwarf planet rather than just another asteroid. Its composition appears to be a mixture of rock and ice, and there are hints that it may once have harbored, or may still harbor, pockets of briny liquid deep below its surface. Spacecraft have revealed bright patches on Ceres's dark, dusty surface, especially in certain craters. These bright areas are thought to be deposits of salts left behind when salty water from below seeped up and then evaporated or sublimated, leaving reflective minerals behind. The craters themselves are reminders of impacts, but the bright spots tell a quieter story of internal processes and slow chemical changes. From our vantage point, Ceres is a dim, round world drifting in its own slow orbit, neither a full-sized planet nor a simple rock, but something in between, a small, complex world in a quiet neighborhood of space. Many asteroids are not solid mountains of rock, but loose piles of rubble barely held together by gravity. Close-up images of some asteroids show irregular shapes, covered in boulders and dust. These bodies may have formed when larger objects were shattered by impacts and then slowly reassembled under their own weak gravity. Instead of being solid all the way through, they are more like floating heaps of fragments with empty spaces between the pieces. Because their gravity is so gentle, the rules of motion on these asteroids are different from what we are used to. A rock that tumbles down a slope might bounce away into space instead of coming to rest. A spacecraft can touch down, sample material, and then leap away with a small push from its engines. The landscapes are rugged, but the forces are soft. In the darkness between the major planets, these rubble piles drift, turning slowly, warmed and cooled by the distant sun, changing only gradually over millions of years. Far beyond the asteroid belt, a giant planet waits. Jupiter, a world so large it could hold more than 1,000 Earths inside. As we leave the last scattered rocks of the belt behind, Jupiter becomes the dominant presence ahead. First it is a bright star, then a disk, and then a vast striped globe filling our view. Its diameter is more than 11 times that of Earth, and its mass is more than twice that of all the other planets combined. It is the largest planet in the solar system by a wide margin. Jupiter orbits the Sun at about 5 times Earth's distance, taking almost 12 Earth years to complete one circuit. Despite this long year, the planet spins rapidly on its axis, turning once in just about 10 hours. This fast rotation stretches its clouds into bands, creating the characteristic striped pattern we see in images. From our imaginary ship, drifting in orbit around Jupiter, the planet's bulk fills much of the sky, a constantly changing tapestry of color and motion. Jupiter is a planet made mostly of hydrogen and helium, more like a small star than a big Earth. Unlike the rocky inner planets, Jupiter has no solid surface as we usually think of it. Instead, its upper layers are composed of thick clouds and gas. As you descend into its atmosphere, pressure and temperature increase steadily. Hydrogen, which is a light gas at ordinary conditions, is squeezed into strange states under these enormous pressures, eventually forming a deep layer of liquid and metallic hydrogen that conducts electricity. Somewhere beneath these layers lies a central core of heavier elements, perhaps rock and metal, but it is buried deep under tens of thousands of miles of gas. No spacecraft has ever dived that far down. The surface that we see is really just the tops of clouds, swirling and interacting in patterns shaped by chemistry, heat, and rotation. You can think of Jupiter as a vast, slowly turning sphere of compressed gas, with a hidden heart we can only infer through careful measurement, never observe directly. From space, Jupiter's top clouds are striped with bands and dotted with storms as wide as planets. The broad bands we see are zones and belts, lighter and darker regions where gases rise and fall, flowing in opposite directions. Between them, storms develop, twist, and sometimes merge. The most famous of these is the Great Red Spot, a giant storm that has raged for at least a few hundred years. It is larger than Earth and rotates slowly, like a vast, reddish oval embedded in the planet's southern hemisphere. These storms are not violent in the cinematic sense, with crashing sounds and sudden flashes, but rather slow, persistent systems powered by differences in temperature and composition. They form, they shift, they shrink or grow, and some of them eventually fade away, replaced by new patterns. The entire atmosphere is in motion, but the changes unfold on timescales of days, months, and years. From our orbiting vantage point, we would see the clouds drift and reshape themselves, the Great Red Spot gradually rotating into and out of view, all playing out in a silent ballet of gas and light. Despite its huge size, Jupiter spins faster than any other planet. A day on Jupiter, from one sunrise to the next at a given point on its equator, is just under 10 Earth hours. This rapid rotation causes the planet to bulge slightly at the equator and flatten at the poles. It also helps drive the strong jet streams that shape the cloud bands, contributing to the complex atmospheric patterns we see. Deep inside, the movement of electrically conducting material generates a powerful magnetic field, much stronger than Earth's. This field extends far into space, forming a magnetosphere that dwarfs the planet itself. Within this magnetosphere, charged particles spiral along magnetic field lines, creating intense radiation belts and auroras at Jupiter's poles that would be enormous and bright if we could see them in visible light. All of this, the spinning, the field, the auroras, happens constantly whether we are watching or not. Jupiter turns and hums in its own way, a giant engine of gas and magnetism running quietly in the outer solar system. Jupiter is like a miniature solar system, with dozens of moons circling in its deep gravity well. 4 of these moons are especially large and prominent: Io, Europa, Ganymede, and Callisto, often called the Galilean moons because they were first recorded by Galileo Galilei in the early 17th century. Each of them is a world in its own right with distinct geology and character. Io, the innermost, is the most volcanically active body we know. Its surface is mottled yellow, orange, and black from sulfurous compounds, and dozens of volcanoes spew plumes of gas and dust high above the surface, driven by tidal heating as Jupiter's gravity flexes the moon's interior. Europa, a bit farther out, is smoother and icy, its surface crisscrossed by dark lines and cracks. Beneath its ice shell, evidence strongly suggests the presence of a global ocean of liquid water, kept warm by internal heat. This hidden ocean, sealed away from space, is one of the most intriguing places in the solar system in the search for possible life. Ganymede, the largest moon, is bigger than the planet Mercury. It has a mix of dark, older terrain and lighter, younger grooved regions, and it even has its own magnetic field, a rare trait for a moon. Callisto, the outermost of the four, is heavily cratered and ancient, its surface recording billions of years of impacts with relatively little change. Orbiting Jupiter, these moons form a family of frozen and fiery worlds, all moving together in the planet's deep gravity, each following its own quiet path. Leaving Jupiter feels like gliding away from a silent giant, leaving behind a family of frozen worlds. As our ship's engines nudge us outward again, Jupiter slowly shrinks in the rear window, its bands and storms becoming stripes and then a dot of cream and orange against the black. Its many moons, once large enough to fill our view, now appear as points of light clustered around their planet, then fade as separate glimmers. We pass through regions where small Trojan asteroids share Jupiter's orbit, clustering ahead of and behind the giant planet, like loose groups of pebbles pulled along by its gravity. Beyond that, the space between planets opens up again, wide, dark, and mostly empty, with only the distant sun, Jupiter behind us, and a new pale light ahead. That new light is Saturn, another gas giant, fainter and farther, but bearing one of the most famous features in the entire solar system. Saturn is a pale, golden giant wrapped in the most delicate ring system in the solar system. As we approach, Saturn grows from a yellowish star into a sphere, and then into a globe surrounded by thin, bright rings that encircle its equator. The rings shine because they are made of countless particles of ice and dust, reflecting sunlight in a flat, glowing plane. Depending on our viewing angle, they can look broad and open, or they can thin down to a delicate line, almost invisible when seen edge-on. Saturn itself is slightly smaller than Jupiter but still enormous compared to Earth, with a diameter about 9 times greater than our home planet. It is also made mostly of hydrogen and helium, with a deep, layered interior and a possible solid core at its heart. Like Jupiter, it has bands of clouds, though they are more subtle and softly colored, giving the planet a gentle, creamy appearance. From a distance, Saturn looks like a carefully crafted ornament, a planet dressed with rings, drifting silently around the sun. Saturn is so light for its size that it would float in a bathtub big enough to hold it. On average, Saturn's density is lower than that of liquid water. This is because it is made mostly of light gases, spread out over a large volume. Of course, there is no bathtub big enough, and the conditions inside Saturn are far from gentle water, but the comparison gives a sense of just how airy this giant planet really is compared to solid worlds like Earth or Mars. Saturn spins quickly, completing one rotation in about 10.5 hours. This rapid spin causes the planet to bulge at the equator and flatten at the poles even more than Jupiter does. Its atmosphere shows bands and storm systems, including a peculiar, long-lived hexagonal pattern around the North Pole, a geometric shape formed by winds flowing in a stable, repeating way. In the quiet of space, Saturn's fast rotation and gentle density are just additional rhythms in the background, part of the continuous, intricate motion of the solar system. Up close, Saturn's rings are not solid sheets, but countless icy particles orbiting in thin, delicate bands. The rings span tens of thousands of miles from the planet, but they are remarkably thin, in many places only tens of feet thick. They are composed mainly of water ice, ranging in size from tiny grains to chunks as big as houses, all orbiting Saturn at different distances and speeds. Gaps and divisions in the rings are created by gravitational interactions with Saturn's moons and with clumps of material within the rings themselves. Some small moons even orbit within the edges of the rings, shepherding particles and helping to maintain sharp boundaries. From far away, the rings look smooth and uniform, but from a closer vantage they are intricate and finely structured, with waves, spokes, and braided patterns shaped by gravity and motion. You can imagine drifting just above the ring plane, watching innumerable ice particles glide past in slow, silent arcs, each one a tiny, reflective grain in a vast, celestial disk. Around Saturn, moons of many kinds circle like a family of very different children. Saturn has a large collection of moons, each with its own character. Titan, the largest, has a thick atmosphere richer in organic molecules, with clouds and lakes of liquid methane and ethane on its surface. Its sky would be hazy and orange, its seas dark and cold. A distant echo of the roll water plays on Earth. Enceladus, a much smaller moon, has a bright, icy surface and geysers near its south pole that shoot water vapor and tiny ice grains into space. These plumes suggest a subsurface ocean of liquid water beneath the ice shell, warmed by internal heating. Some of the material from Enceladus's plumes contributes to one of Saturn's faint rings, creating a subtle link between moon and planet. Other moons are darker, more heavily cratered, or oddly shaped, some with two-tone surfaces or strange ridges running along their equators. Together, they make Saturn's neighborhood rich and varied, a cluster of frozen worlds orbiting a giant, gaseous center. As we look back from our moving ship, Saturn's rings and moons form a serene, complex system, turning slowly in the dimmer sunlight far from Earth. Beyond Saturn, the sun shrinks even more, and the darkness deepens from this distance. The sun is no longer the overwhelming light we know from Earth's sky, but a bright star among many, still the brightest but farther and smaller. Yet its gravity continues to bind the planets, moons, asteroids, and comets into one vast system. We have now traveled from the inner rocky worlds, past Mars's deserts and the asteroid belt, through the domains of two giant planets and their many companions. Ahead lie even more distant giants, Uranus and Neptune, and beyond them, the realm of icy dwarf planets and the outermost edges of the sun's influence. Our path continues outward, into regions where the warmth of the sun grows faint and the night becomes deeper and more serene. You don't have to stay awake to follow every step of this journey. You can let your eyes close, let your breathing become slow and steady, and know that this quiet flight through the solar system will keep going whether you are listening or dreaming. While you rest, Jupiter and Saturn continue to turn in their long orbits, their rings and moons circling them endlessly in the dark, as our imaginary ship slips silently toward the far edge of the planetary family. 35. Uranus is a planet that rolls around the sun on its side. As we leave Saturn and its glowing rings behind, another giant appears ahead, dimmer and more distant. Uranus is an ice giant, slightly smaller than Saturn and much less massive, with a soft blue-green color caused by methane in its upper atmosphere. It orbits the sun about 19 times farther out than Earth does, taking roughly 84 Earth years to complete one long, slow circuit. What makes Uranus especially strange is its tilt. Its axis is tipped by about 90 degrees, so instead of spinning like a top that stands upright, it spins more like a rolling ball. One hemisphere can spend decades tilted toward the sun, bathing in a long, slow summer, while the other hemisphere sits in a prolonged twilight winter. Over the course of its long year, the roles gradually reverse. You can picture Uranus as a quietly rolling world, turning on its side in the dark, its seasons measured not in months, but in decades. Around Uranus, faint rings and dark moons circle in an off-kilter system. Uranus does have rings, though they are much darker and thinner than Saturn's brilliant bands. They are made of small particles of rock and ice, likely coated in dark material, which makes them hard to see except when the light catches them at just the right angle. They form a narrow, tilted halo around the planet's equator, which itself is tipped almost sideways relative to the sun. A family of moons travels with Uranus, each following this unusual orientation. Some of the larger ones, Miranda, Ariel, Umbriel, Titania, and Oberon, are icy worlds with surfaces marked by canyons, cliffs, and ancient craters. Miranda, in particular, looks as if it has been torn apart and put back together, with mismatched patches of strange terrain and towering icy cliffs. From our drifting ship, we see Uranus and its moons as a tilted, quiet system, as if someone gently tipped a mobile on its side and left it to rotate slowly in the cold. Farther out still, Neptune circles in the cold, thin sunlight, deep blue and windswept. Neptune is the last of the giant planets, similar in size to Uranus but a more vivid blue, again because of methane and other trace gases in its atmosphere. It orbits the Sun about 30 times farther away than Earth does and takes roughly 165 Earth years to complete a single orbit. While Uranus appears calm from a distance, Neptune's atmosphere shows signs of more active weather. Despite receiving much less sunlight, Neptune has strong winds, some of the fastest in the solar system, racing through its upper atmosphere at speeds that would dwarf any storm on Earth. Dark storm systems, like the once observed Great Dark Spot, appear and fade, drifting through its bands of clouds. These storms come and go over years, forming and dissolving slowly in the thin, cold air. You can imagine Neptune as a deep, sapphire sphere, its winds whispering around the planet in powerful but unhurried patterns, far beyond the warmth you know. Neptune's largest moon, Triton, orbits backward and may be a captured world from beyond. Triton is an unusual moon. It circles Neptune in the opposite direction of the planet's rotation, on an inclined, retrograde orbit. This suggests that Triton did not form where it is now, but was likely captured long ago from the outer reaches of the solar system, perhaps from the population of icy bodies we are about to visit. Triton's surface is pale and bright, made mostly of nitrogen and water ice, with dark patches where other ices and materials are exposed. Despite the intense cold, Triton shows signs of activity. There are smooth plains that appear relatively young and dark streaks that may be the traces of icy geysers, where nitrogen gas and dust are vented from below the surface. Orbiting backward around Neptune, Triton feels like a visitor that found a permanent home, a captured wanderer from the deep outer darkness, now turning slowly in a borrowed orbit. Beyond Neptune, the orderly line of planets gives way to a broad ring of icy worlds. This region is called the Kuiper Belt, a vast zone of small, frozen bodies that extends outward from just beyond Neptune's orbit. These objects are remnants from the early days of the solar system, pieces of icy rock and rock-hard ice that never joined together to form large planets. Many of them are only a few miles across. Some are hundreds of miles wide. 36. The sun is much weaker out here, just a bright star in a very dark sky. Temperatures are extremely low, and the surfaces of these objects are coated with frozen nitrogen, methane, water, and other ices. From a distance, they are simply dim points of light circling the sun on long, slow paths, each one taking centuries to complete a single orbit. We are now in a realm where time stretches and the sun's warmth is a distant memory, a ring of icy remnants tracing out the edges of the planetary family. Pluto, once called the ninth planet, is now understood as one of the largest of these icy neighbors. As our ship glides deeper into the Kuiper Belt, we pass near Pluto, a small, complex world that captured human imagination long before we knew its true nature. Pluto is smaller than Earth's moon, with a diameter a little over 2/3 that of our lunar companion. Its orbit is tilted and stretched, taking it both inside and outside Neptune's path over its long, 248-year journey around the Sun. When a spacecraft flew past Pluto, it revealed a surface far more varied than many expected. There is a large, bright, heart-shaped region of nitrogen ice. Within that heart lies a smooth plain, almost free of craters, suggesting relatively recent geologic activity. Elsewhere, dark regions, rugged highlands, and towering mountains of water ice stand out against smoother plains of frozen nitrogen and methane. Pluto even has a thin, fragile atmosphere of nitrogen that expands and contracts as the dwarf planet moves closer to or farther from the Sun. You can imagine Pluto as a small, distant world with a frozen heart, quietly orbiting in the dim blue-gray light, its surface changing slowly over spans of time, much longer than a human life. Pluto shares a close partnership with its large moon, Charon, and together they almost behave like a double world. Charon is big compared to Pluto, about half its size, and the two bodies orbit a common center of mass that lies between them, not inside Pluto itself. Both are tidally locked, always showing the same face to each other. If you stood on Pluto, Charon would hang in the same place in the sky, never rising or setting, just slowly changing its phase with the sun. Charon's surface is heavily cratered in some regions, with deep canyons and a darker polar cap likely made of processed ices. The connection between Pluto and Charon is more than just gravitational. Material can move between them over time, and their shared orbit is a slow, graceful dance in the dark. When you picture Pluto and Charon together, it may help to think of them not as planet and moon, but as two partners orbiting a point in space between them, circling the sun side by side in the far cold outskirts. Pluto is not alone. It shares this outer realm with other distant dwarfs that rarely make the news. Objects like Eris, Haumea, and Makemake are also large members of the Kuiper Belt and nearby regions. Eris is similar in size to Pluto and orbits even farther out, on a path that takes it through some of the coldest, darkest parts of the solar system. Haumea spins so quickly that it has stretched into an elongated, football-like shape, and it is surrounded by a ring and small moons. Makemake, another distant dwarf, has its own peculiar surface of frozen gases. These worlds are faint and far away, but they remind us that our solar system is more than just a tidy set of 8 planets. It is a collection of many different types of bodies. Giant planets, rocky worlds, dwarf planets, asteroids, and icy remnants, each following its path on timescales that dwarf human history. All of them move in quiet orbits, circling the sun in patient, elongated loops, whether anyone is watching them or not. Some of the icy bodies out here occasionally fall inward and grow tails, becoming comets. When an icy nucleus from the Kuiper Belt or beyond is nudged onto a path that carries it closer to the sun, its frozen surface begins to warm. As it approaches, some of the ices begin to sublimate, turning directly from solid to gas. This gas carries dust with it, forming a glowing coma around the nucleus and long tails that stream away from the sun. One tail is made mostly of dust, spreading out in a curved path that traces the comet's orbit. Another, the ion tail, is made of charged particles pushed directly away from the sun by the solar wind, often forming a straighter, narrower line. From Earth, we sometimes see comets as bright visitors with graceful tails, visible for a few weeks as they sweep through the inner solar